We will be continuing our discussion on conservation of momentum. Now, conservation of momentum is referring to a principle that states that whenever you have two objects in an isolated system, in other words, the two objects are not being affected by any external factors other than themselves, when you have two objects colliding with one another, the initial momentum before, the initial total momentum before they collided equals the final total momentum after they collided. Whatever collective initial momentum they had before they collided, that equals the final total momentum that they have after they collided. Now recall that there are two types of collisions. We have elastic collisions and inelastic collisions. In this video, we'll be talking specifically about what we mean by inelastic collisions. Now, inelastic collisions refers to a situation where you have two objects and in a situation where they collide, in a perfectly inelastic collision, we have a situation where they collide and then they stick to each other, as shown in this animation. So we have two objects going in opposite directions. They meet, collide, and stick to one another, and they move as one unit. So that's one example of a perfectly inelastic collision. Here's another situation. We have a cannonball inside a cannon. Initially, you'll notice that the two objects were together, the two masses were together, both the cannonball and the cannon, and after it was fired, and that's where the collision happened, after it was fired, the two objects separate from each other. And so you'll notice that that's another example of an inelastic collision. Now, note that there is a difference when we're dealing with elastic versus inelastic collisions. In elastic collisions, we stated that both the momentum and the kinetic energy are conserved. In other words, whatever momentum and speeds that both objects had initially, that's how that they're going to actually get that same amount of momentum and kinetic energy after they collide. Now this actually differs when we're dealing with inelastic collisions. And in inelastic collisions, we do still see a conservation in momentum, but when we look at the object's kinetic energy, we do see a change in kinetic energy. So in other words, kinetic energy is not conserved in a inelastic collision. And so if I go back to these examples again on the animation, here in the cannonball situation, you'll notice that the two objects weren't moving before they collided, and then after they collided, in other words, after it ignited and shot the cannonball out, the two objects did move at a certain velocity. So we do see a change in velocity here, and because we do see a change in velocity, we see a change in kinetic energy. And so this is a situation where we have a inelastic collision where both objects moved at a certain velocity after they collided. Now here we do see this principle happening again. You'll notice that the two objects are moving towards each other at a relatively fast pace. But then as they collide and then stick, you notice that they move a little bit slower. So we do see a change in kinetic energy in this situation here. And so we would also call this a perfectly inelastic collision. And so just remember that when we're dealing with inelastic collisions, total momentum is conserved, but the kinetic energy is not conserved. Now, while the momentum of the system is conserved in an inelastic collision, and kinetic energy is not conserved, note that some of that kinetic energy has been transferred into something else. That could be in the form of heat, also known as thermal energy. It could be converted into sound energy, or the energy can be transformed into a situation where it causes the material to deform in some way. And so here we see that energy is not totally lost or completely got eliminated. It did transform into another form of energy. And so when we're looking at kinetic energy specifically, note that we do see either we do see a change in kinetic energy when it comes to inelastic collisions. Let's talk about the equation now for inelastic collisions. Now it looks a little bit as the same as the elastic collisions. However, there is a difference. The equation, first of all, stems from the law of conservation of momentum, where the collective total momentum before the collision equals the collective total momentum after the collision. Note that momentum equals an object's mass times velocity. And so when we put this into perspective in the case of perfectly inelastic collisions, we can write the equation as this: m1v1 plus m2v2 equals m1 plus m2 times v prime. What you're seeing here is the situation where both objects are stuck together. And so m1 plus m2 times v prime represents the two objects sticking together and moving as one velocity. Now notice that I didn't specifically write my initial and final subcharacters in this equation, and that's because that this equation can be used reversibly. In the situation where we're seeing the two objects initially separated from each other, and then when they collide, they stick, we see the situation where both objects were separate initially, and then finally they were together. And so in that situation, we can treat these values on this side of the equation as the initial values because they were separate from each other. And then we can look at this side of the equation as the final values because we now see that that both objects are together, as shown here in this animation. Now in this animation, we see the two objects initially together. And then after collision, we notice that the two objects separate from one another. We see the cannon recoiling in one direction, and we see the cannonball being shot out at a totally different direction. But as you can see, initially they were together. And so the equation can be looked at the other way around, where this would be considered the initial components because the two masses were together, and this part of the equation can be signified as the final components because we do see the cannon and the cannonball separating from one another after they collided, as shown like this. And so just note that the equation can be written as such, but just know that this is the final equation, or this is the main equation that you would need to know whenever you're dealing with objects undergoing a perfectly inelastic collision. So this is the inelastic collision equation.